I'm going to start off with the, okay, last problem set. So we'll take a quiz on this pretty soon, and then we'll have a test, and then we'll move on to the third unit, which has a whole bunch of other interesting stuff involving derivatives. And then second semester, we'll start talking about antiderivatives. That'll be interesting. Okay, this says consider the position time graph below. Okay. All right, Lillian, can you listen to this, please? Can you just humor me? Pay attention to this. Okay. So position versus time. So there's a little vocabulary here that you got to know. You might not be familiar with. Velocity. Oh yeah. What's the difference between velocity and speed? Who can tell us that? Very good. So velocity can be negative. It's like that film with a guy. His name's Vector. He has magnitude and direction. Okay, so you can be positive or you can be negative for velocity. Okay, so that's the only difference. If you want to be mathematical, you can make a simple statement like speed by definition is just the absolute value of velocity. That says it all right there. That's everything you have to know about speed and velocity. So if we're ranking the velocities, which spot on there, well, actually, let's clarify something else. This might not be obvious, but when you measure something like speed, if we're talking about where are you in terms of position, feet, versus time, we're talking feet per second would be the velocity or the speed. That makes sense? So we're talking about rate of change. So if this guy was in like a little tiny car or something, his speedometer would be telling you the speed at any given moment in time. So in this case, suppose I made up numbers. Let's say he started off at position 10 feet. And let's say this minimum position was like 1 foot. Well, he went basically backward. He went to the left 9 feet over some small period of time. So, but what we're concerned with for calculus is instantaneous rates of change. So it's the difference between, you guys remember average rate of change? One of my examples for average rate of change was if I drive my car, let's say 100 feet in 4 seconds, right? Then my average rate of change would be 100 divided by 4, 25 feet per second. But does that mean that I was going instantaneously the same speed the entire time? No, I might have been going 30 feet per second and then 15 feet per second, right? I could have been slowing up and speeding down. So anyway, all we're looking at here is these tangent lines to know the instantaneous velocities, how fast we're going. So sorry, this video, hopefully, I think I find if I don't stand, somehow the video eventually, yeah, okay, there we go. Now you can kind of see it. Okay, so anyway, where's the velocity the greatest? C.
Oh, positive. Yeah, C.
Let's take care of this. A would be the biggest speed. Notice he's going really fast at A. He's rapidly changing position over a small period of time, but he's going left. That's a negative velocity, okay? So in terms of velocities, A is actually going to be the least value because it's the most negative number. And then let's see, so C seems to be the most positive. Who's the next most positive after C?
B.
Probably B. E's negative. So D looks like it's probably 0, but 0 is a greater value than like negative something. So my ranking for the velocities is C's the greatest, then B, then D, then E, then A. For the speeds, though, I would be taking basically treat everything like this was positive. Well, if A was like -10, then that's the biggest value in there. So after A, it's kind of a toss-up between B and E. I'm sorry, no, C's the biggest. I'm sorry. Yeah, C clearly is more slopey than. The next one is maybe ambiguous. Is E or B bigger? I'm not sure. I don't know. Let's just say E. Doesn't really matter. As long as you get the idea, it's fine. And then D is the smallest. In terms of speed, the smallest number you can ever be is 0, right? Okay, are there any questions on the distinction between speed and velocity? If there are, you're going to be super confused going forward. You sure we get it? Okay, great. All right, so answer. All right, take 10 seconds here, rank them, and then see if you have an idea about how we could calculate those two values. So anyway, go ahead, answer those. We'll check our answer in a sec.
Oh my gosh, it's Babbage.
Oh God, Jesse, no.
What? This is my favorite part of physics. Well, he calls average speed savage because he writes an S and then ABG. But I call average velocity Babbage because it's BABG. Babbage.
That's pretty good. That's pretty good.
Yeah, good stuff.
Mr. Paul's triggered already.
No.
Deep breaths, Mr. Hall. You can go talk to your therapist.
Yeah, pull yourself up by your bootstraps.
Okay, so you guys get the ranking. At what point is the velocity the greatest? A. So it goes A. A is the greatest velocity. Then who's next? B, C, D. For speeds, D looks a bit steeper. Yeah, it's negative, but it's actually the fastest speed. I know C is going to be the last. It's 0. And then A looks like it's more slopier than B. Slop. Okay, so there's my ranking. All right, now, does anyone have an idea how we could maybe calculate the average velocity for the whole trip?
Take all the numbers and divide it by 4.
It's not a bad idea. The problem with that is it's discrete. So you are, in theory though, it's actually a great idea. So suppose you calculated the speed at 0, the speed at 1, the speed at 2, the speed at 3, the speed at 4, the speed at 5, the speed at 6, the speed at 7, the speed at 8, and then you average them all up, you'd probably get reasonably close to the average. Did I say speed? I should have said velocity, I'm sorry. But you guys see what I'm talking about?
Yeah.
Positive velocity, positive velocity. Eventually it's 0 velocity. And then you get a lot of these like pretty strong negative velocities. But the problem with that is you'd go, well, wait a second. I mean, you're ignoring stuff like, what about the time interval between 1 and 2? Don't you have to account for that? Then you say, okay, fine. We'll go 0, 0.5, 1, 1.5, 2, 2.5. And of course, their objection to that is, well, you missed a whole bunch of spots again. So what's really interesting is in what we're going to do here is actually equivalent to adding up an infinite number of velocities and averaging them, but it's way simpler than that. Yeah, the definition of average velocity would be how much displacement do you have over how much time took place. Now, these little symbols, that's a delta.
No, that's a fine.
Delta.
I'm just kidding.
So displacement, if you want a definition for displacement is just the difference between your final position and your initial position.
Yeah.
So in this case, I started at position 0 and I ended at position 0 over this time interval. So my displacement is 0 feet. And that took 8 seconds. And so 0 feet per second is my average velocity. This is savage. Does that make sense? Okay, so this is a very important definition.
Georgie.
Oh, Mr.
yeah.
George! They sent you back?
Yep. Sorry, I wouldn't be able to be back.
George.
That's lit. Okay, I think I need it.
So what is the?
It's so hard to see on that smart board thingy. So, what's up?
What does X mean? Does X mean like? the
Position.
And then E is this
Yeah, so notation wise, that's a good question. So X represents the position. So imagine this, let's also clarify something else here. What this is talking about is a lot of people, so this is position in meters. Oh, did I say feet? I'm sorry. It was meters. My bad. My bad, guys.
Imperial stuff.
Time is in seconds. A lot of people get confused and they think that this graph is talking about someone traveling in this arc path. That's not at all what it's describing. It's describing something moving along a single one-dimensional axis. Where did this guy start? What position?
0.
So imagine a number line where we started at position 0. Where was the farthest position we got to? We walked over to position 3 meters. So we walked 3 meters to the right. And then what did we do over that last 2 seconds roughly? We came back. So here I'll perform it for you. Here's this graph in poetry in motion. Okay, so I went faster on the second one because, see, he was going pretty slow. He stopped for about 2 seconds, and then he came back pretty fast. That make sense? This is one-dimensional motion. Okay, so anyway, yes, X represents your position. The T, of course, represents